Hi everyone. Today we come to the last part of learning unit 4, which is acid-base equilibria. And in this part I will discuss with you two main topic, which is one, the buffer solution, and second one, the combination between weak acid and weak base. All right. Without further ado, let me explain what is a buffer solution. A buffer solution is a solution which resists a pH change when you add in a small amount of hydroxide ion, or in other words base, or H plus ions, or in other words acid, into the solution. Meaning to say that when you add a small amount of acid or base into a buffer solution, the pH will not change. Okay. A buffer solution consists of a mixture of a weak acid, which we can call it HX, and its conjugate base, which we can call it X. So the dissociation reaction between in a weak acid, it can be represented by HX in aqueous solution, which dissociates into H plus ion, and also its conjugate base X. We have learned in our previous lecture on the Ka expression, which is commonly used for expressing a dissociation constant for an acid. We call it as acid constant or acid dissociation constant, acid equilibrium constant, and many more terms which is similar to that. So in this case, if you remember Ka, it's equal to the concentration of H plus ion times the concentration of the conjugate base divided by the concentration of acid at equilibrium. Okay, so in this case, our weak acid in a buffer is called HX formula. Okay, we represent it by using HX. So Ka would be the concentration of H plus ion times the concentration of its conjugate base divided by the concentration of the weak acid. So if we want to find the concentration of H plus ion in our buffer, we can use this Ka expression, which is the concentration of H plus ion equal to Ka times the concentration of weak acid divided by the concentration of its conjugate base. If the HX to X ratio remains more or less constant, the pH in a buffer solution is not significantly changed. How does this happen? Let me explain to you by using the diagram here. Okay, if you add a base to a buffer solution, the hydrogen ion concentration decreases by less than the amount of expected of the quantity of base added. Meaning to say that the acid and its conjugate base consume the hydroxide ion here. Okay, and the pH of the solution does not rise significantly, which it would rise significantly if you don't add buffer in the solution. So if you look at the representation of it in diagram here, you can see that the hydroxide ion bind with the acid and base inside the weak acid and the base inside the buffer solution. But you can see also there are some more ions here are not bind to anything, okay? Not bind to any hydroxide ion. So meaning to say that there are still some capacity of the buffer which can retain the pH, the initial pH of the solution. Okay, so what happens if we add some amount of acid into a buffer solution? What happened? Okay, of course, when you add acid to a buffer solution, you are adding or introducing H plus ion into the solution. So when a strong acid in the form of in the form of H plus ion or hydronium ion is added to a buffer solution, okay, we have the conjugate base present in the buffer, which consumes the H plus ion or the hydronium ion, H3O plus. Okay, and converting it into water and the weak acid of the conjugate base. Okay, so this results in a decrease in the amount of conjugate base present in the solution and increase the amount of weak acid. However, if you look at the diagram here, you can see there are some more ions which is not bind to any H plus ion or any hydronium ion. So you know that there is still a capacity for this buffer to retain the pH of its initial solution. So this is what actually happened when we have um, a buffer solution and how it can retain pH although we add a small amount of acid or base into it. Okay, so this is called buffer capacity. Buffer capacity refers to the amount of acid or base that can be neutralized by the buffer before there is a significant change in the pH. As we have discussed just now, whenever we add base or acid into a buffer solution, it will not change the pH, but somehow there is a limit to this buffering capacity. Okay, this is what we call as buffer capacity. It refers to the amount of acid or base which can be neutralized by the buffer before there is any significant change in the pH of the solution. So the greater the amounts of conjugate acid-base pair, the greater the buffer capacity. Okay. So the pH of the buffer depends on Ka. What is again Ka? Ka is the acid constant. Okay, and it can be represented by an equation that we call as Henderson-Hasselbalch equation. So whenever you are dealing with problems, analytical chemistry problems regarding pH of a buffer solution, buffer capacity, finding the concentration of a buffer capacity, and so on. Finding concentration of a buffer and so on, you should use the Henderson-Hasselbalch equation. Okay, so Henderson-Hasselbalch equation is expressed as negative log H plus ion equal to negative log Ka minus negative log concentration of the weak acid divided by the concentration of the conjugate base. Or simply, this is more simple to remember, pH equal to pKa plus log concentration of the conjugate base divided by the concentration of weak acid. So most of the time, I think it is easier to remember the pH expression of Henderson-Hasselbalch equation compared to the negative log H plus expression of Henderson-Hasselbalch equation. So please bear in mind on the Henderson-Hasselbalch equation for a buffer, we have another alternative expression of Henderson-Hasselbalch equation for POH. Okay, so let me share with you here. POH is equal to PKB plus log, okay, like this. Okay, right? Okay, so this is another expression for Henderson-Hasselbalch equation. Again, pH equal to pKa plus log concentration of the conjugate base divided by the concentration of the weak acid. Okay. Let's look at the example of calculation for buffer, which will utilize Henderson-Hasselbalch equation. Okay. Now the question asked, calculate the pH of a buffer containing 0.1 molar ammonia and 0.2 molar ammonium chloride, whereby Kb for ammonia is 1.8 times 10 to the power of negative 5. The conjugate acid for ammonia is the ammonium, and its Ka is equal to Kw divided by Kb for ammonia. Okay, so you know that Kw equals to Ka Kb. We learned this in the first part of our lecture. Okay, so from here, you know what is Ka. Ka is Kw minus by Kb. Sorry, not minus, divided by Kb. Okay. Why do we want to find Ka in this case? Because in the question, you are given Kb. Okay, but what you want to find in this question is the pH. Remember the Henderson-Hasselbalch equation for a buffer, pH equal to pKa plus log concentration of the conjugate base, which is X, divided by the concentration of HX, which is the weak acid. Okay, go back to this equation. Always, when you get questions for when you get questions for a buffer, from the question, you want to find pH. You don't know what is pH, but from Kb, you can calculate Ka. Okay, so which is, you find it here, from Kw equals to Ka/Kb. And then you know the concentration of the conjugate base, which is, what is the concentration of conjugate base, which is 0.1. Okay, ammonia is the conjugate base, and the weak acid is the ammonium, which is 0.2. Okay, so you just substitute all the value into the Henderson-Hasselbalch equation, and you will find the pH for your buffer solution. So the solution here is with pH at 0.95. So you know that the buffer solution is in basic condition because the buffer contains the weak base ammonia and its salts ammonium chloride. Okay. All right. So you may ask me whether you can solve this question by using the pOH expression of Henderson-Hasselbalch equation, since it is given in the question Kb. Of course, you can use it, no problem. It's just that at the end of this calculation, if you use pOH expression, you will get value for pOH. So remember, if you get value for pOH, you must use the formula pH equal to 14 minus pOH. Only then you can find the pH. You will get the same answer, which is 8.95. Okay, so no problem. Okay. Now let's look at another question. A buffer is prepared by adding 45 ml of 0.15 molar sodium fluoride to 35 ml of 0.1 molar HF. What is the pH of the final solution? So in this case, your buffer consists of NaF and also HF, and you are given Ka. Okay, what you can do here, you can straight away write the Henderson-Hasselbalch equation, which is pH equal to pKa plus log concentration of the conjugate base divided by the concentration of weak acid. Okay. So pH here, what do you want to know is the pH. You don't know what is the pH, but you have information for Ka. So P here means, what does P means? P means negative log. So remember, P function always means negative log. Okay, so you can substitute Ka here, and you substitute the value for X and Hx. And you will get the answer 3.43. So this is the solution. Okay, it's just straightforward application of the Henderson-Hasselbalch equation. All right. Note that here the conjugate base is 0.08 molar and the acid is 0.044 molar. So when NaF and HF are mixed, in this case, dilution is involved. So the concentration of NaF is no longer 0.5. It's given in the question that the concentration of NaF is 0.15 molar and the concentration of HF is 0.1 molar. So what happened when you add together 45 ml of NaF with 35 ml of HF? Of course, the total concentration, the total volume for the resulting buffer should be 45 ml plus 35 ml. Okay, so here we'll get 80 ml of buffer solution. What happens if the buffer solution has more volume compared to the original solution that you use to prepare the buffer? It means that the original concentration of the species that you use to make the buffer solution will decrease. Okay, why? You go back to the expression for a number of mole, which is N equal to mv. Okay, so mv, m1 v1 equal to m2 v2. In this case, because when the preparation of buffer is happening, it involves dilution. Why dilution? Because you have the resulting volume larger compared to the original volume of each of the species, whether the weak acid or the conjugate base species. Okay, so you have to recalculate what is the concentration for both NaF in buffer and HF in buffer. Okay, you have to recalculate. Okay, so when you have recalculate, you can see that you get this concentration 0.08 and 0.04. Okay, how you recalculate? You use M1 V1 equals to M2 V2. So you calculate both HF and also you calculate for NaF. Okay, using the same formula. M2 V2. So you know what is V2, which is 80 mil. You know is V2 80 mil. 80 mil. Okay, but this one is the original volume. This one is the original concentration. You want to find the resulting concentration. This is what you want to find, the concentration of both species in the buffer solution. Okay. Okay, that's how you get this number 0.08 and 0.04. Just because when any sorry, what happened to my screen? Okay, just because when any preparation of buffer is made, you have a mixture between the weak acid and its conjugate base, and dilution is involved, so the concentration of your species is no longer the same as the original concentration. Okay, so you have to recalculate the new concentration. However, if there is question which is asking you that to ignore any volume change. For example, in this question here, let me see which question. Let's say like example 12 here. It is asking you to ignore the volume change due to the addition of the conjugate base. Okay, so in this case, you just use the original concentration. Sorry, not concentration. You or use the original volume. So there is no change in concentration of your species in the buffer solution. Okay, so in some cases you are asked to ignore the volume change, but in some cases, if it is not stated that you should ignore the volume change, you cannot ignore the volume change and you have to recalculate the new concentration of both weak acid and conjugate base in the buffer solution. All right. Okay, let's look at example 10. What is the pH of a buffer solution that is 0.1 molar ammonia and 0.1 molar ammonium ammonium salt, okay, or conjugate base here, okay, ammonium. Conjugate acid, this is the conjugate acid and this is the weak base. Okay. What is the pH? So you directly use the Henderson-Hasselbalch equation. So in this case, it is using the pOH expression for Henderson-Hasselbalch equation. As I have mentioned just now, it doesn't matter whether you use pH expression or pOH expression. It's just that you have to take note what the question is asking you, whether it asking you the pH or it's asking you the pOH. So either using the pOH expression or pH expression, the final answers should consider what is asked. So in this case, if you use pOH, you need to again, at the end of the calculation, convert the pOH into pH. Okay, by using pH equal to 14 minus pOH. Okay. Now, let's look at how we are going to solve this question. If you use the Henderson-Hasselbalch equation, in this case, it is given Kb for ammonia is 1.8 times 10 to the power negative 5. And you have all this information, you just put it into the equation. So you can get the value for pOH. So to get the value for pH, 14 minus the pOH. So 4.74 is the pOH. So you get the pH 9.26. Again, you see that this buffer solution is a base in a basic condition. Okay, because you can see here the main species is the NH3 as the base and the ammonium salt is as the conjugate acid. Okay, so from this example and another example that we have discussed just now, we know that buffer solution not only can consist of weak acid combination with its conjugate base, but also weak base combination with its conjugate acid. Okay. All right. Now let's discuss the solution to example 10 number 2. Okay. It's asking you what is the pH if 12 ml of 0.2 molar hydrochloric acid is added to the buffer. Okay, you have prepared this buffer, you already know the pH, and now the problem is you want to add a small amount of acid, a strong acid, which is HCl, hydrochloric acid, to the buffer. Okay, and when you add hydrochloric acid to the buffer, The final volume is 125 ml. Okay. So after the addition of 12 ml of 0.2 molar HCl, so this is the equation. You have HCl reacting with NH3. HCl is an acid and NH3 is a base. So it will result in the concentration of ammonium ion, okay, with the chloride ion. Okay, so HCl will reduce the amount of NH3 present, okay, because it reacts with NH3, okay, and it increases the amount of NH4 plus, okay. So it will increase the amount of NH4 plus. So this one will reduce. Let me use another color. This one will reduce, minus, and this one will be increased, plus, okay, right. Now, let's calculate the number of mole of ammonia reacting with hydrochloric acid. Okay, so what is number of mole of HCl added? It's 0.2 molar times 12 mil. So this is M and this is V. It equals to N, which is number of moles. This is the volume. Okay. So you have 0.0024 mole. Okay. And what is happening to the resulting concentration of ammonia? We know just now that when HCl comes into the buffer solution, it reacts with the ammonia in the buffer solution. So when it reacts with the ammonia in the buffer solution, it reduces the amount or the concentration, the number of moles of um, NH3 or ammonia in the buffer solution. So we know that the resulting concentration of the ammonia would be smaller compared to the initial concentration of ammonia. So how to calculate this? You go back to the expression N equals to MV. So you need to calculate the number of moles for NH3 by subtracting the number of moles initially present in NH3 minus the number of moles reacting with hydrochloric acid, which you have calculated just now, 0.0024 mole, divided by the total volume of the solution. It is mentioned in the question just now for number 2, for example 10.2, the resulting volume of the buffer plus HCl is 0.125 liter. Okay, or 125 mil, you convert it to liter. Okay, so you get the answer for concentration of the resulting NH3. Okay, and then what happened to the resulting ammonium salt? It will increase. Okay, the concentration will increase. As has been discussed just now. So in this case, you have to calculate the new concentration, which is number of moles initially present plus the number of moles reacting, the number of mole HCl reacted with NH3, okay, which is 0.0024 divided by the total volume. You get this answer. And then replace all the values into the Henderson-Hasselbalch equation. In this case, you have the information for PKB, so you can use the POH expression for Henderson-Hasselbalch equation. But after that, you need to convert it back to pH by using pH equals to 14 minus POH. Okay. Example 11, this is quite straightforward. What is the pH of a buffer solution that is 0.1 molar chloroacetic acid and 0.15 molar sodium chloroacetate? So it's obvious here the buffer solution is a combination of a weak acid and also its conjugate base. And you are given Ka. First of all, you need to write down the Henderson-Hasselbalch equation, pH equal to pKa plus log concentration of conjugate base divided by the concentration of acid. Okay, sorry about the lagging in screen. All right. So you just substitute all the value inside the equation and you get the final answer pH equal to 3.03. Okay. Now let's look at example number 12. How many moles of sodium acetate must be added to 2 liter of 0.1 molar acetic acid to give a solution that has a pH equal to 5? So ignore the volume change, meaning to say that you don't have to recalculate the new molarity of each species, okay, due to the addition of sodium acetate. So Ka is given. So what you should do is you just replace everything in the Henderson-Hasselbalch equation. So pH equal to pKa plus log concentration of the conjugate base, or you can also use X. Okay, X divided by the concentration of acid. So you have pH, which is 5. You have P function, which means negative log. You have Ka given, which is 1.7 times 10 to the power negative 5. And then you have log. You don't know what is the concentration of the conjugate base. Okay, you are not given the concentration of the conjugate base, but you are given the concentration of the acid. Okay, you are given the concentration of acid, which is 0.1 molar. Okay, all right, so rearranging the equation, equal to 5 plus log. Okay, so after you have finish calculating this, you will get 0.2304. So what you want to do is anti-log 0.2304. Okay, and then you will get the concentration of conjugate base, which is 0.1699. Okay, from here you can calculate the mole. Okay, I don't have enough space, so I put it here. N equal to mv. In this case, you know what is your concentration of your conjugate base, which is 0.1699 molar times with the volume, which is 2, because there is no change in volume. So you get the final answer is 0.34 mole. Okay. Right, so that's about it for example 12. Now, let's discuss a bit about polyprotic acid, although we are not going to do or to learn any calculation problem regarding polyprotic acid, but it's important for every one of us to understand what is polyprotic acid. Okay, so polyprotic acid is the acid that have more than one ionizable proton. For example, if you have HCl, it is called a monoprotic acid because it only have one ionizable H. Okay, one ionizable proton. This is monoprotic. Polyprotic. So what about H2SO4? This is called this is a polyprotic acid, or we call it diprotic acid because it has two. Di means here two. Two ionizable proton. Yeah, there are two ionizable proton. What happen if we have H3PO4, phosphoric acid? So this is also a polyprotic acid. The same with H2SO4. They are polyprotic acid because they have more than one ionizable proton. In this case, for phosphoric acid, you have three ionizable proton. Okay. So when we have more than one ionizable proton, these protons are not released all together at one time. Okay. They are not released all at once. They are removed or released from the solution, or they dissociate, or they ionize. These are all the same terms. Okay, they have the same meanings. They ionizes in steps, one by one. Okay, how they choose the H plus to be released one by one? Which one will go first? Okay, um, it is always easier to remove the first proton in a polyprotic acid than the second. Therefore, the release or the dissociation of the proton in polyprotic acid depends on the Ka, or acid dissociation constant, of each H available in the polyprotic acid. For example, in the case of H2SO3, the first H ionized has Ka of 1.7 times 10 to the power negative 2. Compared to the second H, it has Ka of 6.4 times 10 to the power negative 8. Which one is lower? Ka for the first proton or Ka for the second proton? So if you look at the value here, Ka for the second proton is lower. So you know that which H will be released first? The H which have higher Ka. So we can have this sequence in release of the proton from a polyprotic acid. Remember, the proton with higher Ka will be released first and then followed by the lower Ka, and so on. Okay. Alright, that's about it on polyprotic acid. Now we move to acid-base properties of salt solution. Nearly all salts are strong electrolytes. So if you look at the things that you have learned in electrochemistry chapter in a general chemistry topic, you know that all salts are strong electrolytes. Okay, and therefore salts exist entirely as ions in a solution. So acid-base properties of salt are a consequence of the reaction of the ions in the solution. So the ions in the salt solution are reacting, so it causes the salt to have acid-base properties. Okay, so the reaction in which ions produce H plus or hydroxide ion in water is called hydrolysis. So anions from weak acid should be basic. Okay, and anions from strong acids are neutral. Okay, so you remember this. The anions from a weak acid are basic, and anions from strong acids are neutral. Okay. If the conjugate base comes from a weak acid, then the pH of the solution can be calculated using the equilibrium expression. Dissociation of the conjugate base in water results in the product in the form of HX, which is the weak acid, and also the hydroxide ion. some metal ions react in solution to lower pH. And let's see what is the combined effect of a cation and anion in a solution. So an anion from a strong acid has no acid-base properties. Why? Because we have learned just now that all anions from a strong acid, it is neutral. So because it is neutral, it has no acid-base properties. However, anion that comes from the weak acid, they are basic condition. That's why they are called conjugate base. Okay, so any anion that is the conjugate base of a weak acid will cause an increase in pH. Of course, because base is always has higher pH, okay, more than 7. So the existence, the appearance of conjugate base in a weak acid will cause the increase in pH. The cation, that is the conjugate acid of a weak base, will cause decrease in pH because it is in an acid, conjugate base. Conjugate acid. Okay. Metal ions will cause a decrease in pH. So remember, metal ions will cause a decrease in pH except for the alkali metals and alkaline earth metals. Okay, so these are metals from periodic table, the first the first the first column element, the second one, and the second one, alkaline earth metal. So when a solution contains both cation and anions from weak acid and bases, you need to use the Ka and Kb expression, Ka and Kb value to determine the final pH of the solution, because both the solution contains weak acid and bases. Okay, you need to consider the Ka and Kb. Now, if you look at the question here, example 13, calculate the pH of a 0.1 molar ammonium chloride solution. The Kb value for ammonia is 1.8 times 10 to the power negative 5. In this case, take note that the major species in solution are the ammonium ion, chloride ion, and water. Okay, so we note that both ammonium ion and water can produce H+. You still remember the term auto-ionization of water? So we know that H2O can also generate H+ ion. Okay. So in this case, you want the pH of ammonium chloride solution. So the main species here that you want to deal with is the ammonium ion. So we have ammonium ion dissociating in water, resulting in ammonia and also hydronium ion. Okay, or it doesn't matter, H+ ion, it doesn't matter. Okay, so here you use the Kw equal to Ka-Kb expression. Okay, this is what we learned in the first part of the learning unit 4. From here, you can get Ka because you were given in the question Kb. You were given Kb. However, you want to find ammonium ion, which is the acid component of this solution. So you want to use Ka. You find Ka first. From there, you use Ka expression, which is Ka equals to concentration of the conjugate base divided, times concentration of hydronium ion divided by the concentration of the acid. Okay, so if you still remember in the second part of the learning unit 4, we have learned about Ka formula. Okay, so Ka is always the concentration of H plus ion or hydronium ion is the same. Okay. Times concentration of the conjugate base divided by the concentration of acid. Okay, so this is what you want to remember forever, okay, as a chemist. So Ka is equal to this. So you replace everything according to your dissociation reaction. So Ka equals to concentration of NH3 times concentration of hydronium ion divided by the concentration of NH4. You already have Ka and you already have the concentration of ammonium from the question, which is 0.1 molar. And you need to find X. From X here, you can get the pH. What is X? X here is the concentration of, again, this one, the hydronium ion, and the concentration of the conjugate base. Okay, so they are the same concentration. So X times X. So you get this concentration and you use pH equal to negative log H plus concentration. Yeah, in this case, hydronium ion concentration. Okay, so you get the answer. Example 14. Calculate the pH of a 0.3 molar sodium fluoride solution. So the Ka value for HF is 7.2 times 10 to the power negative 4. So we note that the major species in this solution are NaF and H2O. Okay. We want to find the pH of NaF. So the major species here, we are dealing with Na plus and F negative. So here we write the dissociation reaction. NaF in water dissociates into NaOH and also HF. You are given Ka for HF, which is a part of the solution. Okay, but you want to convert it into Kb because NaF is the base. Okay. So from there you have Kb. Kb equals to the concentration of the conjugate base divided by the times the concentration of the H plus ion divided by the concentration of the acid. Okay. All right. Sorry. You substitute Kb here and then you get POH. From POH, you find pH. pH equal to 14 minus POH. Okay. So this is Kb. Kb expression. Alright, so this is all about it for the last part of learning unit 4, which is acid-base equilibria. After this, we will continue with learning unit 5, acid-base titration. And hopefully, what you learn in learning unit 4, the important one is about Ka. How do you calculate Ka? What is the relationship between Kw, Ka, and Kb? The ability to convert the P function into negative log, or when to use the anti-log function. Okay, you have to know that. You have to know that when you deal with a buffer solution, you need to use the Henderson-Hasselbalch equation. And when you are required to find any pH of a species in a mixture of cation and anion in a solution, you should be able to identify which is the major part of the solution. How do you know which one is the major part?
you look at the main thing which is asked by the question, which pH it is asking for. Okay, you know that you have to consider dissociation for that particular species. Okay, and you have also to take note that whenever you have a mixture of weak acid with its conjugate base to form a buffer solution, or a combination of weak base and its conjugate acid to form a buffer solution, you have to really carefully see if the question is asking you to ignore any new volume change after the addition of the species in the buffer, or you need to recalculate the molarity based on the new total volume. Okay, take note of that. So I hope you can do all the tutorial and also study questions given. Try to use all the concepts that we learn in this lecture. So thank you very much. If you have any questions, you can contact me. Okay, bye.